Hello everyone, welcome back to another lecture. I hope everybody's doing fine and you can watch these videos to catch up with chapter 3 content of the calculus course. So we talk about section 3.2 today. The title is Maxima and Minima. We want to talk about some points called maximum points, minimum points. And at the end of the day, maximum points, minimum points are points on the graph of a function. I have a part of the graph of a function as you see here. I have plotted some points which I'm going to talk about them. Point A has coordinates of 3, 1. Point B 5, 6, just in case you can't read because it's small. Point C is 7, 4. Point D 9, 11, and point E is 12, 3. We have a whole bunch of points. But if you look at these points, starting with point A, what name would you give to this point A? The name, it makes sense to be an endpoint because we are restricting part of the graph of a function from x equals 3 up to x equals 12. So this is the left side endpoint, point A. The other one is the right side endpoint within this interval. So if I have listed all the points and I want to describe these points, I'm going to call point A an endpoint. So that's one description for now. And there is another endpoint, and that's endpoint E right there. So point A, point E on far left-hand side, far right-hand side of this portion of the graph of a function are called endpoints. Nothing, complicated. But if you look at point B, and if you look at a neighborhood of point B, that point B is the point with the highest y-coordinate. If you look at the points a little bit to the right, a little bit to the left of point B, none of those points have a y-coordinate of 6 as point B has. So to the right of B, there is a whole bunch of points, but their y-coordinates are probably 5.9, 5.8, maybe 5.7. On the left-hand side, the y-coordinates would be around again 5.6, 5.7. But the only point with the highest y value is point B, whose y-coordinate is 6. So because the y-coordinate of this point is the greatest value in a neighborhood of point B, we call this a maximum point. All right? So point B is called a maximum point, or better to say local maximum point. I'm going to name this point local max point, or sometimes it's also known as relative maximum point. So relative maximum point or local max point. Because relatively speaking, or locally speaking, at a neighborhood of point B, this point has the highest y-coordinate. That's why we call it locally, local maximum point. Imagine, for example, in our school, somebody gets the highest mark in the calculus course. Somebody gets, let's say, 95%, right? So locally speaking, relative to the students in our school, in our community only, that student has a mark of 95%, let's say. But does that mean that this student has got the highest mark in the whole province of Ontario or in the whole country of Canada? No, there might be other students with higher averages. So this is not the absolute maximum point. It's not the point on the graph that has the highest ever y-coordinate, but locally speaking, yes, it has the highest y-coordinate. In our school, yes, that student X has got a mark of 95%, but we have other students in other schools, probably other cities, whose averages could be even higher than the average of that student in our school. So these kind of points with the absolute maximum y value are known as absolute maximum points, such as point D. So point D is called an absolute maximum point. Okay, why? Because if you look from point A to point E, that is the only point whose y-coordinate is the highest ever, and that's 11 actually. Look at these other points. Nobody has the highest y value of 11 that point D has. So point D is called absolute max point, but point B is called local max point. Now point C, similarly, is a point that has the lowest y coordinate actually at a neighborhood of point C. The y coordinate is actually 4. So a bit to the right of 4 could be 4.5, a bit to the left could be 4.6 or 4. Maybe 9 or 4.1, but nobody has the lowest y coordinate as point C has, and that is actually y equals 4. So we call point C local minimum point. So local minimum point, or we can call it relative minimum point. I'm just looking for some point which would have absolutely the lowest y value. And I look at point E, we have y coordinate of 3. Point D is our question, that was absolute max point. Point C has a y coordinate of 4, it's a local minimum point. Point B was a local max. But if I look at the end point on the left-hand side, that is point A, I see the y coordinate is 1, and that is the smallest ever, the least y coordinate I can find among all these points on the graph of this function y equals f of x. So I'm going to call this endpoint actually my relative minimum point or local minimum point. So not only point A is an endpoint, but also it is a local minimum point as well. All right. So it is possible for a local minimum point to be an endpoint, in other words. So now that we know these terminologies, we're going to talk about some definitions, easy definitions. Critical number of a function. What is a critical number? A critical number function is a number at which either f prime at that point is 0. So if I call the critical number, let's say C, then f prime at C is either 0 or f prime at C does not exist. Okay? That means that the derivative is not defined at x equals C. There are two examples that would show this to you. If I have a polynomial function here, it's a cubic function. If I take the derivative, that will be 3x squared plus 12x plus 9. You know this very well. And then I'm going to set this equal to 0, actually. And this step is very important. Why? Because think about these local maximum minimum points. Because if you draw a tangent line at these local maximum or local minimum points, what do you think the slope of those tangents will be? The slope of tangent is actually 0. Why? Because the tangent lines are horizontal. And if the tangent line is horizontal and slope is 0, it means that y prime is actually 0 at this local maximum point or even at this local minimum point. Even at the local maximum point, it is possible for y prime to be 0. Nobody says no. So this step is important. If you want to find critical numbers of a function where f prime at C is 0, you have to set y prime equal to 0 all the time. And then you end up with 3 times x squared plus 4x plus 3. I just factor 3 out. And this is a quadratic equation. You can easily solve it. I would say 3 times 1 is 3. Add them up 4. So I quickly factored it. Now, if you set each factor equal to 0, you get x equals negative 3 and x equals negative 1. And these two x values are known as the critical numbers of the function. So there's two critical numbers for this cubic function that we found. Why are these critical numbers? Because those are C values, those are X values, such that f prime at those values, -3 and -1, happens to be equal to 0. Okay? The second case is when f prime does not exist, and this is another example. It's not a cubic function this time. And if I want to differentiate this, just like before, I have to apply the product rule probably. So the root of first times second, that would be 2/3 of x to the exponent of -1/3 times the second plus the root of second, which is 1 times first. That would be cube root of x squared. And then if I set y prime equal to 0, let's see what we end up with. If I multiply, I get 2/3 of x to the exponent of 2/3 plus 12 thirds. So 12 thirds is actually 4. I'm going to reduce the fraction. That's going to be 4x to the exponent of -1/3. And finally, x to the exponent of 2/3. So if I collect like terms, I end up with 5/3 of x to the exponent of 2/3 plus 4 times x to the exponent of -1/3. If it's small, I'm just reading it for you, and you can watch the video 10 million times as you wish. So I end up with this simplified form of y prime. And perhaps I can rewrite this as 5 cube root of x squared over 3 plus 4 divided by cube root of x. And now I can find the common denominator. So that will be 3 cube root of x. So in the top, I end up with 5x and plus 4 times 3, I believe, which is 12. So why bother? I'm going to write 12 here. Okay. So now if I set this equal to 0, what do we end up with here? So to continue, I will erase this part because we don't have enough room. So we end up with this result. Y prime equals 5x plus 12 divided by 3 times cube root of x. Now, if you set y prime equal to 0, of course, the numerator will be set equal to 0, from where x would be -12/5. And this is actually one of the critical numbers. I'm not saying no. But then if you look at the denominator, if x is 0, then y prime would be 12 divided by 0. And 12 divided by 0 is clearly undefined, which means that y prime equals dne actually at x equals 0. Now, don't forget that the function itself is defined at x equals 0. Nothing is wrong. The graph of this function passes through the origin. X equals 0, y equals 0 satisfies the equation. So it's not like the function is undefined at x equals 0. On the contrary, the function is actually defined at x equals 0. But the derivative does not exist because of this cube root of x in the denominator. So if x is 0, cube root of x would be 0, the denominator will be 0, the whole fraction or the y prime becomes undefined. And as a result, x equals 0 becomes a critical number. So once again, we ended up having two critical numbers. One is -12/5, the other one is x equals 0. But these two are critical numbers for different reasons. Don't forget that. The first one is the critical number because f prime is 0 at -12/5. The other one is a critical number because f prime doesn't exist, not because f prime is 0 at x equals 0. So to wrap up, there's a theorem known as Fermat's theorem. It says if f of x has a local maximum or minimum at x equals c, then either f prime at c equals 0 or f prime at c equals dne. So actually what we talked about earlier is in the form of an official theorem known as Fermat's theorem in calculus. Okay. In the next lectures, I'll try to give you more numerical examples. Okay, thank you.